Dr. Kuhn received his PhD in physics from Princeton University and is currently a professor and astronomer at the University of Hawaii's Institute for Astronomy. Kuhn is well known for his leading work in the development of numerous innovative astronomical telescope and instrumentation projects, and for his service on many astronomy and space physics advisory boards. Some of these include chairing the AURA Solar Observatory Council. AURA is the Association of Universities for Research in Astronomy that staff the national observatories. Chairing the Advanced Technology Solar Telescope Council, what we now know is DKIST, the 4-meter solar telescope being built out in Hawaii. Scientific Advising Committee for the New Jersey Institute of Technology Center for Solar and Terrestrial Research, of which Big Bear Solar Observatory is a part. The 2000 Decadal Survey Science Committee in Astrophysics. The NASA Roadmap Committee. The Breakthrough Foundation Watch Advisory Board. The Planets Telescope Foundation, which I believe we'll be hearing much more about tonight. The Scientific Advising Committee for the Keppenhauer, excuse my pronunciation, Institute for Solar Physics in Germany. I know I alliterate that pronunciation every time. Tonight, Dr. Kuhn will be speaking on concepts and techniques for searching for life on exoplanets and potential hardware that could actually accomplish it. Please join me in welcoming Dr. Jeff Kuhn.
So, hi everybody. It's a wonder that I ever get any work done in that introduction. So this is my first time giving an interactive talk over Skype. Let's hope the technology is up to it. In an effort to try to be as interactive as we can. So you see me looking off to the side because that's where I see you. On the other screen is my talk. Don't be distracted by that. But I hope that if you have any questions as we go through it, please don't be shy, and Claude will help facilitate getting answers. We're raising points as we go. Okay, so a lot of what I've been interested in over the years are optics and optics technologies. And this first slide is just an image that this is kind of the bottom line in this talk, is that we have in our hands the technology now to be able to do some really interesting questions. And so the next slide is a picture of some of the people that have been working on the technology and the arguments to make this happen. They're mostly a bunch of engineers and scientists with a sprinkling of astronomers in it. So this group, funded by a private investor, and you can't really see him on the bottom picture there. He's the smiley guy on the left side of the red table, 3 people deep. That's Casey Harlington. He got all of this started about 4 years ago with a little bit of money that brought this group together to work on the question of, well, if you had to start from scratch, how would you go out and find life in the universe? Okay? And so what I'm going to talk about are the burning questions that guide. ELF is our acronym for an Exo-Life Finder instrument. I want to tell you what a post-ket ground-based ELF could look like and the technologies that make these telescopes possible. So, are we special? Another byline to this talk is that, so I was born roughly 60 years ago, and my mother spent the first 1 or 2 years of my life convincing me that I was special in a very restricted sense in a small universe. And I think that we spend our lives, most of it anyway, getting through the notion that actually we're not special. And I think that's part of the problem that we have with our civilization and the way we look at existence. That human life is not special, just like as you've learned, or scientists have learned over the last 25 years, that exoplanets are not at all special, and even exo-Earths are not special. So in the next slide, this is a plot that shows on one axis the temperature of a star in a system that includes a known exoplanet. It's an old slide. There are many more now that are known. And on the horizontal axis, our understanding of the distance in astronomical units of that planet away from the star. And Earth is shown by that blue marble in here. And that gray line shows where planets would be that could have water, just on average. And the point of this slide is just to show two things. One is that there are lots and lots of exoplanets. And two is that Earth is not at all very special, that in terms of where it lies in the distribution, and there are lots of systematic effects. Most of this data comes from Kepler. And it's all public. If you just go to the Kepler website, you can learn more than I know about exoplanets. But we're not very special as an exoplanet goes. So in the next slide, I just wanted to make the point that we're a bunch of scientists and engineers, but we think that, you know, this old problem that was made famous by Enrico Fermi sort of 60 years ago, which was that, well, how is it the Milky Way isn't actually all that big. It takes only, say, a few million years for a signal to propagate across the Milky Way, whereas life on the Earth has existed for almost 4 billion years, as we know it. Why haven't we seen any evidence, since that timescale for a signal to propagate is so short compared to the timescale with which life has existed? Why haven't we seen any evidence that there is life? And of course, that's launched lots of searches for extraterrestrial intelligence, this Fermi paradox. The Fermi paradox says that, well, I mean, the naive conclusion is that life is very rare and precious and fragile, and the only place in the universe where it exists. I completely reject that, and people that I work with do also. SETI hasn't seen a signal, and we haven't seen the lizard people here on Earth, because the energy barrier to getting from one star to the next is enormous. And it's really never going to happen. The most likely thing, if we're going to send ourselves to another planet, is that we send our genetic code and we print ourselves into the DNA there. But long ago, in the 60s, there was actually a lot of reputable scientific thought devoted to trying to understand what life outside of the Earth could look like. And what's really surprising is that was going on at a time when I was a graduate student, I was taught that it's just exceedingly rare to have conditions around a star that would produce a planet. And up until 25 years ago, we believed that that exoplanets would hardly ever exist, and certainly exoplanets that could have conditions like Earth that could support liquid water were really hard. Of course, that turns out to be completely wrong, and the foresight of folks 50 years ago in trying to understand and classify exolife, I don't think I'll go through it, but just to point out that lots of folks believed in the 60s, especially in Russia, that we should begin to think about what life could look like in the universe. And that was before we knew what we know now. So the next slide just summarizes what some of the important ways of finding life might be. So these are called biomarkers. If you could look out at a planet and find evidence of life, the typical kind of signals that you might look for if it's primitive plant life is you could look for so in the lower graph it shows the edge of photosynthetic molecules, where they work and where they don't. And so if you could go out and look at all of this relies on capturing the light of the exoplanet, right? Either by reflected light from the star or by, in some cases, by the light which is actually radiated by the exoplanet. But a lot of work has been done in trying to understand what the signature of life in the presence of water would look like. And we won't go through that, but the presence of oxygen, ozone, and methane are all gases that in general are non-equilibrium. They exist in our atmosphere because photosynthesis and animals create them. And so to be able to look at a planet and see that from a distance is a pretty powerful indication of life. Well, there's a exoplanet in particular that we want to think about. So in the next slide, and Claude, I think that this is actually animated, but on the right-hand panel is an image of Alpha Centauri, A and B, and Proxima Centauri, which is a speck that you can't really make out. And if you blow it up, you get to see an artist's picture on the left side of the red dwarf star. And
we have that on the screen.
It's on the screen? Okay. And what an exoplanet might look like. And in the distance, Alpha Centauri A and B. So I wasn't shocked, but I think a lot of people a year and a half or 2 years ago were shocked when the very closest star to the sun, once we got enough technology to be able to look at it carefully enough, had a potentially water-bearing planet on it. So Proxima Centauri is the very nearest star to us. It's 3 or 4 light years away. And by Doppler analysis, it appears to have a planet very close to the star, but at a distance from this much cooler star where liquid water could exist. Now there's some rumors that maybe the data doesn't quite support this and the jury is still out, but it is a powerful statement that our ability to see just how unspecial we are is evolving with our technology to see the world around us. And of course, part of the answer to why Fermi's paradox doesn't tell us that life is extremely rare is that we haven't really had the capability of finding life on nearby exoplanets. Okay, so the next slide reveals something that was a kind of a shock to me, which is that maybe the best biomarker for life is to look for the heat signature of life. So here's something which is almost universal, which is that life in general is all about converting the free energy of the heat around us into into something that moves and eats and behaves like life does, reproduces. So here's a calculation you can do. If you were to take the total power that humanity uses and divide it by the total power that the Earth intercepts from the sun, so think of that total power as a total power in terawatts, and the total power that on average humanity uses, what fraction of that power, the total power that the Earth intercepts from the sun, are we now consuming? Any ideas? Well, if the slide is up there. Yeah, there you go. It's a surprise. It's like 0.05% of the total solar energy that strikes the Earth we are now using by various means. I found this to be a shockingly large number, and so 0.05% of the total solar power is being created and used by humanity. Okay, so now why does that bother you? What happens to all of that power which is used? Where does it end up? It has to end up as heat. So ultimately, all of that power also becomes heat. So at the level of 0.05%, we have an unavoidable global warming problem, which has nothing to do with ozone, which just has to do with the fact that we use more and more power, and as we use it, it gets dumped into the environment as heat. And we can't refrigerate our way out of this, right? No. It's like opening the door in your refrigerator in your kitchen because you want to cool the house. So the other interesting fact is that if you go back in time, the total fraction of the power was less on that log scale. And there are larger fractions, the photosynthetic global power consumption. So this is the power that goes into storing energy that plants essentially do, right? Plants absorb sunlight and create chemical reservoirs of that energy, which we're now using as coal and oil. That's an even larger fraction. On this graph, I think the number is about 3 or 4%. So these are big numbers, and they suggest that maybe the way to find a universal marker for life is a thermal signal. And it turns out that the answer is yes. That is a fabulous way to look for life. If we were to look at a planet like the Earth far away and watch the Los Angeles area rotate into view, the average temperature of Los Angeles, just the thermal energy that it radiates, you know how much warmer it is than the background of the surface of the Earth? The Los Angeles civilization on average is a few percent warmer than the average thermal energy that the Earth produces. So the Earth is at a temperature of about 270 degrees Kelvin, or 20 degrees Celsius, or 70 degrees Fahrenheit, whatever it is. It radiates energy into space. When Los Angeles rotates across the limb of the Earth so that we could see it from space, if you were out in space, there would be a measurable increase in the infrared brightness where heat energy is radiated. So that was one of our early compelling arguments to say, look, detecting life isn't all that hard if you can detect light from an exoplanet, which means detecting the thermal signal created. And you may know that thermal energy is at a temperature of a few hundred degrees Kelvin is best detected at what wavelengths? 10 microns, 5 microns. So when Arnold Schwarzenegger in the Predator movies was looking at his prey, they were glowing in a 10 micron camera. And that's where we want to find the signature of life on exoplanets, by looking at Los Angeles as it rotates across the field of view. I don't know if we want to go through this, but this was an optimistic view of how life emerges on a planet. It either emerges and it's successful, in which case it's observable from the time it emerges until now, or it's not successful.
Okay, what slide are we on now?
We are on slide 10. I am on slide 10. Where are you?
I have an image of a planet that soon will be possible to find life outside the solar system.
Yeah, okay, so that's just for show. Go to the next one.
Oh, okay, there we are. I don't have numbers on the slides, so.
I'm sorry. I'll try to be more cogent about moving on. So this was an attempt to take the Drake equation and update it and put things that we know in a different form. And if you believe that life emerges and that we're not special, then you can do a calculation to estimate how many stars do you have to look at that could have life on them, and by that I mean that could have liquid water. How many do you have to look at before you have something statistically interesting to say about whether life is survivable? All right, so here's the point. Imagine you could look at enough exoplanets, determine whether there's life there, and in effect do a census for life around us. You could imagine that if you never saw life on any of those planets, that would be pretty bleak, especially if you believe that we're not so special. If you did see life on those planets, you might say, well, we have something to learn about how we can survive on the Earth. So this is an equation that just renovates the Drake idea in terms of the number of planets in the habitable zone, and the idea that last term on the right is the fraction of successful civilizations. What is the probability that a civilization here is going to be measured by its heat output, appears and can last for a long time, at least until we appear on the scene and can measure them. So the next slide puts numbers on that. So that box in blue there is an interesting result, at least to me. And what it says is that the number of detections of life should equal 38 times the probability that a civilization, once it emerges, actually survives. Okay, so if we, and this is based on the telescope concept that we called Colossus, they could see 600 stars in the neighborhood of the Earth that could have potential Earth-like planets. So if we looked at all 600 of those stars and we found none that had life, we would conclude that F sub s is smaller than 1 over 38. In other words, the probability that any civilization succeeds once it emerges, based on these simple ideas, is pretty remote. It's a few percent. On the other hand, if you believe that we're not special, and it's a 50-50 chance that once life emerges that it reaches a point where it can survive, then this equation says that we should, if F sub s is 50%, then this is 19, then we should be able to find lots of life around us. All right, so what's the point of this? This says that if you build a telescope and you can look at a few hundred stars, you ought to find evidence of life if our hypothesis that we're not special is meaningful. Okay, so how do we do that? So let's go to the next slide. And so this is a little bit of optical science, which we don't need to go through, but here's the problem. You got this really bright star, which may be millions or even billions of times brighter than the exoplanet, and you want to separate the light of the exoplanet, or the heat signature of the exoplanet, from the light of the star. What does that depend on in terms of the telescope that you're going to use to see, if you had a perfect telescope? Well, it turns out that detecting this very faint signal in the presence of a large background depends on the diameter of the telescope to the 4th power. So that means that if you're going to detect this signal in a telescope which is twice as big, it will take you only 1/16 of the time to see that signal. Well, that's really good if you can build big telescopes. It's not really good if you believe you can build a really good telescope on the ground and you were going to compare it to space. So I put this slide up to point out that the problems we're talking about are going to be done on the ground. They're not going to be done in space. We can talk about building telescopes that are tens of meters across, and we have to compare even the JWST. Anybody know how big that is?
6.5 meters.
Right. It's a 6.5 meter telescope, and the 30-meter telescope. Anybody know how big that is? It's actually 30 meters.
Anybody?
So you compare a 6.5 meter telescope, the 30-meter telescope turns out, I think, won't do the problems we're talking about here, but a telescope that was 30 meters across, in principle, would be 6.5 times what? About 4 is roughly 30. 4 times 4 times 4. That telescope on the ground would be 256 times better at seeing exoplanet light than a telescope in space. So while NASA is interested in other problems, the general problem of doing a census or seeing enough stars to be able to quantitatively address this question of Fermi's paradox needs a really big telescope. And anybody know the cost increment for, say you got an instrument that costs you $1 million on the ground, you know how much it costs if you put it in space?
At least 3 orders of magnitude.
Yeah, it's like a factor of 100 to 1,000. So we're going to talk about optics that are maybe $100 million to build. In space, they're $100 billion. And not even JWST is yet $100 billion at 600. So the other thing that happens with big telescopes is that the problem we're trying to solve, which is to separate the light of the exoplanet from the light of the star, depends on what we call the diffraction limit of the telescope. And the diffraction limit of the telescope at some optical wavelength gets better as the diameter of the telescope goes up. So if you wanted to do a census, it depends on seeing a certain volume of space. And if you see further out, then that volume has increased by that distance out cubed. That's the volume effect. So we need to see a number of planets, and the number of planets depends on the volume that we're able to see to. And that's another effect then that scales like the diameter of the telescope cubed. So there are big factors in this problem that tell us that we need a big telescope and this is going to be done on the ground. Okay, so the next slide shows you an example of what the astronomical community is now engaged in. The 30-meter telescope might get built in Hawaii. Actually, the court case is being argued today in Honolulu. The Magellan telescope was already built 4 of their mirrors. They want to build this in the southern hemisphere. The extremely large European telescope, the ELT, is a roughly 40-meter telescope, also being built in the south. And for a long time, astronomers wanted to build the overwhelmingly large telescope, the OWL, at 100 meters. But probably about 6 or 7 years ago, people stopped talking seriously about this because it was more than $10 billion. And then in space, we talk about JWST, which might get launched soon, and projects like LUVAR, which are designed to look for exoplanets. And so there is a reason to go to space. You know what the reasons are? Well, one is we keep a lot of people employed in space technology, but the other is that we don't have to deal with the atmosphere and the absorption of the atmosphere. So there's some advantage to that. The other reason is that we don't have to do adaptive optics. But, so those calculations that I showed you, d to the 4th, 1 over d to the 4th, and d cubed, assume that we have the ability to do, we can correct the wavefront due to the atmosphere. But a real problem is on the next slide, which is that, so here's an analogy you could take with you. If you took one of those high-intensity spotlights and you put it in New York, and you put like a pencil lead next to that high-intensity light, or actually just put a firefly next to the high-intensity light. Detecting the firefly against the glare of the high-intensity light from California to New York is the problem that we're trying to solve. And the glare of seeing through the windshield of these car lights is really a pale problem in comparison to this one. And the next slide shows the telescopes that we want to build. And I don't know if that's animated or not. Looks like it is.
Oh, it is. I just clicked again.
So the underlying slide shows current telescopes and proposed telescopes. And the issue for the 30-meter and the 39-meter telescopes are that they have literally hundreds, almost 1,000 mirrors in them. Lots of edges in the mirrors. and those are bad. And the mirrors and the telescopes we want to build in part are different because they have mirrors as big as you can make them. And so the scale of what we're talking about is illustrated by the big telescope in the middle, which is for doing a census, and the telescope on the right, which is for finding life around the nearest exoplanet called ELF. If we could build it, so I want to talk about ELF now. That's a telescope which is about 30 meters across. It's about like the 30-meter telescope, except it has much bigger mirrors and it's built in a very different way. And the next slide, I want you to think about, imagine that there was an Earth around Proxima Centauri. Might look something like this. So that's the continental structure. The oceans reflect light a lot differently than land or snow or desert or forest. But as the Earth rotates and orbits around the star, this is what we would see from space. So even though we're talking about building big telescopes, a big telescope can never make out the detail that you see in these pictures. We could never take a picture of Earth directly and see the continents and the oceans. The best we can do with a telescope that's even 100 meters across, the Colossus, is to separate the light of the Earth from the light of the star. And we could just, it's like having one pixel placed on the planet. We could measure the total light that's reflected by the planet back towards us. And that's the interesting number. That
I got behind on the slides for a moment. Could we go back to the previous slide that shows the ELT and the Colossus?
So this is just the outline of the mirrors. The bird's eye view of current and planned Keck-era telescopes.
Yeah, here's the current and proposed telescopes with the large binocular in the middle, extremely large telescope off to the right. Okay, now if you could say a word about Colossus and ELF over on the...
Sure. Okay, so now when you animate the slide, on top of all of those telescopes is a telescope that we think we could build for less than $1.5 billion. It's called the Colossus. And it uses the technology ideas that we're going to talk about here pretty quick. We don't think we're going to find $1.5 billion from Yuri Milner and the Starshot Foundation. For about $100 million, or maybe even less, we could build a telescope called ELF on the right, which is a bunch of mirrors that are each about 5 meters across, and there are probably about 19 of them arranged in a circle. So that's the telescope I want to talk about now. And so, in the next slide, I'm just reminding you of what the Earth would look like rotating and orbiting around a planet, around a star rather. And we're thinking now about Proxima Centauri, which is about 4 light years away, and a planet that could be like the Earth. So even with the biggest telescope, Colossus, we wouldn't be able to make pictures like this. All we would do is to be able to, during the course of the orbit of the planet and its rotation, we could measure the total amount of light which is reflected from the Earth. Right? And it's obvious that it changes. And as the Earth rotates, it presents a different amount of ocean and a different amount of landmass, which reflects a different amount of light back towards us in our ELF telescope. Right? Okay, so in the next slide, we've simulated what that, so look at the graph on the bottom. So from 0 to 1 corresponds to 1 exoplanet Earth-like year. And the small scale up and down dips, what do you suppose those are due to?
Rotation.
Those are the rotation. Those are the daily rotation of the planet, and that also changes the brightness that we observe as different things rotate into our field of view. Now, why is it that over the course of the year that the daily variation isn't always the same?
Well, at one point it's going to be on the far side of the star, the other is seeing the illuminated side. On the back side, you're seeing the back side of the planet, I would think.
Yeah. Although you get to see the front side and the back side during the course of the day, right?
Well, yeah.
The summer in the northern hemisphere is brighter than the summer in the southern hemisphere.
Yeah, so this planet is got its rotation axis inclined, right? So that inclination of the axis from 90 degrees means that as you go from summer to winter, the inclination produces a different emphasis on northern hemisphere or southern hemisphere illumination. Okay? But basically, it's just you integrate the light that's reflected off of the planet and you see this variation. Well, what's really amazing is that you can build what's called an inversion computer model, and you can take just those measurements and deduce what's reflecting a lot and what's not reflecting a lot on the planet. Okay, so on the right-hand side is the computer's understanding of the surface of the exoplanet, which is just a map of the Earth at low resolution. It's black where there isn't very much reflection because that's where the water is. It's very green and bluish up near the poles because that's where there's a lot of ice. It's highly reflective. And if you take the data, which is just this time sequence of total reflected light, and turn the computer loose, we can reconstruct the picture down below. In other words, even though we don't have angular resolution to make a picture, we can make a picture over a period of time with a dedicated set of observations that just measure this brightness. So that's an example of what's called an inversion. And it was a little shocking to me that we could make pictures with this much detail. We could see subcontinental structure. So this is our poster child for why we want to build a 30-meter ELF telescope. With a 30-meter ELF telescope, if we can get a signal to noise of about 100, signal to noise means you have enough photons, you have enough collecting area, enough detail in those up and down points to be able to make this inversion, then we can make pictures of exoplanets. We could see Los Angeles over on the coast as a hotspot if we were making thermal observations. And we could see desert regions and jungles and a lot more detail by looking at the wavelength dependence of this. So there's a lot more that you can do with this data. Okay, so next slide just quantifies that. So the signal to noise of the measurement is the magic number. You get lots of signal and not very much noise, and then the fidelity of making this inversion and making the detailed map improves. And as a function of diameter of the telescope, that's the horizontal axis, and for different wavelengths is the vertical set of colored curves, and on the left-hand side is the signal-to-noise ratio. So if you had a few $100 million that you wanted to spend on a telescope, and I came to you and said, we want to make pictures of the nearest exoplanets and look for life, how big should we make the telescope? Well, there's kind of a need there, right? The signal to noise is going up at all colors, and it reaches kind of a plateau, sort of, maybe, over 20 meters. There's a fairly well-defined size that we need to be at, which is 20 to 30 meters, and that's why the ELF is 20 to 30 meters.
Question?
Yeah.
Why does the J-band lag behind the others? It looks like in others, the further you go red, the steeper the curve is until you get to the J-band, which kind of lags at the lower apertures.
Yeah, you would ask that question. Well, all right, so a couple things. One is so the jaggedness of that curve is because the interpolation, I think it's the way we interpolated the set of data that we had for modeling it. The lag and the peculiarity in that has to do with the J-band atmospheric things that are going on, I think. I don't have a short answer to your question.
That's fine.
But you're right, it is quite noticeable. J-band, for some cases, can actually have a little, there's an extinction effect, I think, that is at work there in the atmosphere, and it may be that we haven't modeled it very well too. Okay, so that's all good. These are all ideal telescopes. How could it be? So the TMT, the 30-meter telescope, why don't we just wait for that to get built and then do this problem, maybe look for life around the nearest exoplanets? Well, the answer is that it's a problem with scattered light, as I showed you, but it's also a problem in being able to make mirrors in big telescopes. And so the next slide kind of summarizes what we know about making big optics. Okay, so along the horizontal axis is a plot of the size of the mirror from 10 meters to 100 meters on the right, and that's a linear scale. And then on the left axis, the vertical axis, is the weight of these telescopes. And so the 30-meter telescope is 30 meters diameter, and it weighs the moving mass, that part of the optics that you have to point, is at 1,400 tons, and the cost is actually more like $2 billion. The Owl telescope was 11,000 tons, and it was in excess of $10 billion. And the Keck telescopes are 10 meters, and they're sort of 270 tons. It's well known that the cost of building these telescopes pretty much depends on the mass. The more it weighs, the more it costs. And the mass pretty much depends on the area of the mirror, at least for modern telescopes like these. And so the mass that you have to move around turns out to be about 2 tons. That's that red box. It's 2,000 kilograms per square meter of area in the mirror. If we're going to build a large telescope dedicated to this, it has to have a low mass, and it can't scale like Keck-era telescopes. So that's what we've done. That's where this group has been working the last few years, to show that we should build telescopes differently. And let me summarize those ideas in the next slide. So the idea is that, you know what makes things, so a telescope has to bring light to a focus with mirrors, and those mirrors have to be incredibly accurately placed, and the shape of the mirror can't change, and you know how accurately they have to be shaped to a fraction of a wavelength. The problem is that when you take something which can't deform and you put it on a telescope, what is your enemy? What creates a problem in deforming the optics so they don't work? Well, gravity is the main thing. You're moving the telescope and pointing at it. You have to at different parts of the sky. You have to make it stiff enough so that it doesn't deform. And you make optics stiff by what? By making the mirrors thick, or by putting lots of steel in the back of them to make them stiff. That's the problem with the telescope. That's what makes it heavy and massive and ultimately expensive, is it has to have a figure that's very accurate. So this group, the Colossus group or the Planets Foundation, says, well, let's not make telescopes that way. Let's not make a single uniform shape. So a 30-meter telescope has to maintain its shape over 30 meters against the bad effects of gravity that wants to try and deform it as you move it. Make telescopes on a floppy structure, a structure that can bounce around. If you do that, then actually you save a lot of mass. And the truth is that to make a 30-meter telescope a rigid structure is defeated ultimately if you're building a telescope that corrects for the atmosphere. Because the atmosphere changes the arrival time of light on the mirrors just like a floppy structure does. So one of the issues for the TMT and the other telescopes is that they spend a lot of money and energy on massive structures to be stiff, And then they spend a lot of money and energy to correct the atmosphere, which has the same effect of having of being a not stiff structure. So this is called an interferometric telescope. It is a telescope where each element in those 19 mirror segments in that picture you see there are essentially a separate telescope, and we correct for the floppiness of the structure and the effects of the atmosphere using a bunch of little tiny mirrors that in a minute I'll show you in a movie live up in the upper top cap of that structure. And in the figure down below, it shows the blue rays reflecting off of a bunch of mirrors, and then they converge at the center. Each one of those mirrors has its own little secondary mirror, and they come together to a focus down below. This is an example of we call a hybrid telescope interferometer. We combine the effects of floppy structure that allows us to decrease the mass, and then an optical system that corrects with little tiny mirrors for the phasing of those elements. All right, so now we're getting into the specialized stuff. I apologize for that, but I just want to say a couple more things to get you a sense of how it works. If you were to build a telescope that was floppy in the third panel down from the top, you would produce an image of a star that doesn't look like a single star, but it looks like many, many stars, and they're all faint, and those are called speckles. So even though each telescope can produce a perfect image, when you combine them in this hybrid telescope, the first thing that happens is you get this speckle image pattern. But now when you turn on the interferometer properties of the telescope, all of those speckles come together and you get the right-hand side of the third panel. You get a tiny, tightly focused spot of light, which is what we need to be able to see the exoplanet light. Okay, so finally, the technology to be able to build these telescopes with $100 million instead of $1 billion or more dollars is we have to find a way of making the glass mirrors themselves less massive. And so we said a minute ago that you make a mirror stiff, right, by putting a lot of glass in it. If you use a lot less, so the ultimate mirror is just a thin sheet of glass and then a coating of aluminum, right? What's wrong with that? What happens? Why doesn't that work very well?
It deforms under its own weight.
It deforms under its own weight, and then it will change its deformation as it tracks. But ideally, you'd like to be able to create stiffness, not with mass. Okay, so that's an energy argument. If you figure out how much deformation energy due to gravity exists, it's now possible to put that much energy into a mirror with what are called electroactive polymers. They're like piezos. They're like piezos. They're like crystals, except they can be coated with like a 3D technology onto the back surface of the mirror with some electrodes, and you can put enough energy in that electroactive polymer that's comparable to the deformation energy of gravity for a thin mirror. What it means is you can replace mass with electroactive polymer electrostatic energy. Well, all right, so that's where the real magic in this lies. And then the next picture, the next slide, just shows you how we've done some of the modeling to take big mirrors that could be as big as even 5 meters across, that are only a few millimeters thick. And we never polish the mirror. We never rub on it and grind it. We measure the surface on small scales, and then on the back surface of the mirror, we coat, using a big electroactive polymer printing machine, the right pattern of electrodes that, when they're energized, deform the surface to create what is a uniform, we want a parabola for the optics. So that takes care of the small, so it's window glass. So go out and buy some window glass. Window glass is fabulous on scales that are smaller than a few centimeters. It's smoother than any astronomical mirror. Astronomical mirrors are ground on, and they have a property called micro-roughness, because you're basically fracturing the surface and then undoing that fracturing. If you never abrasively polish a mirror, you have something which is wonderfully smooth. But as you know, a piece of window glass on scales of centimeters is convoluted and not optical at all. So we take those uncertainties out by one layer of electroactive polymer on the back, and this just shows a picture that simulates how we make bumps on the mirror, or we make anti-bumps on another mirror. And we take another layer that produces the overall curvature. And it turns out that up to a size of about 5 meters, for reasonable voltages and reasonable electroactive polymers, we can create the overall shape that we need to focus the light.
Now, these electroactive polymers, is this something that already actually exists and has been demonstrated on smaller optics?
Yeah, let's see, I think I have a picture in one of the later slides. So we're working with a group in Lyon, which is a laboratory just devoted to studies of polymers and their mechanical and electrical properties. It's called terpolymer, and it looks like saran wrap. You wouldn't be able to distinguish it from saran wrap. It's a little bit more expensive, but it's it's not fabulously expensive. The cost of we can get to that, but it's about 200 microns thick, and then you put an aluminum electrode on both sides, and then you shape it to compensate for the unfriendly shape of the window glass that you started with. And it exists, and we're building in the lab actuators and systems that deform the glass just to prove that our computer models aren't crazy. But we haven't yet built a complete mirror, and that's the next step. Let's see what the next slide shows. So, so the bottom right shows a 500 gram mass that's being. This was actually a movie. I don't think it's a movie here, but it's being raised and lowered by terpolymer, which is just to show that we can create a significant amount of force for electric fields. Electric fields are measured in volts per micron that are something like 10 volts per micron. The slide on the left is the other piece of technology that we've been working hard on, and that is we have to get this glass close to the paraboloidal shape that makes it a mirror. Right? Flat glass doesn't help us much. A parabola or a segment of a parabola, a piece of a parabola is what each one of these mirrors has to look like. And so we've worked out this scheme for we call it deterministic slumping, but it turns out there's an equation, a well-defined equation that defines the deformation of a plate. And one solution to the deformation of a plate is exactly a parabola if you set the pressure behind the plate equal to a certain value compared to the mass and density of the glass. So we take a piece of glass, we put it in a kiln, we change the elasticity of the glass by bringing it close to the melting point. It slumps, it forms something close to a parabola, and then we print the electroactive polymer on it to generate the final mirror shape. So the two ingredients to making mirrors lightweight is to use 3D printing and electroactive polymers for small-scale changes and then the overall shape. But to get close to the parabola, we say to get to within the dynamic range of the terpolymer, we do this slumping thing. So that's done in a kiln in our labs here. Okay, one more trick. So there's something really magic that happens when you have a telescope, which is really an interferometer.
Next slide.
Next slide, yeah. So let's see. So on the top you see a bird's eye view of each of the mirrors, right? And then on the slide underneath it, you see, this is called a logarithmic scale, that this is what a single star would look like, but over 6 orders of magnitude of brightness. Okay, so that because this collection of 5-meter sub-apertures that are arranged in a circle isn't just a complete circle, a single picture doesn't produce a simple airy ring, but something that's a little bit more complicated. The star is at the center, and on the right-hand side is a plot that shows it shows you the cut, a vertical cut through the brightness of this. Okay, here's the magic. So when we build optical systems, the pattern of brightness that a star creates is called its diffraction pattern. And you like to think of a telescope as taking all of the light of a star and putting it into just a point at the center of the field. It doesn't actually do that. If there's no atmosphere, it makes rings around it. Those are airy rings, and that's called the diffraction pattern. When you build an optical telescope where you can change the phase of each of the elements, so if you push the animation button on that, the phases will change. So in that circular ring, you see the different colors correspond to a different phase. What that just means is that that light from different elements of that optic arrive at the focus at a slightly different time. And we've computed how to make them arrive at a slightly different time, so the diffraction pattern of the telescope is changed. It still is basically an airy problem, an airy pattern, rings around the brightest point in the very center, but do you see what it's done by changing the phases? It's made a dark spot in the diffraction pattern by adjusting those phases. Why do we want to make a dark spot in our diffraction pattern?
What about the star?
We've just built a coronagraph, a very special coronagraph, which makes a dark spot. And what are you going to put in the middle of that dark spot when you look at the bright star with the next?
Star.
Well, you could put the star, but ideally the star is going to be at the center, and the exoplanet is going to be in that dark hole. So the scattered light of the star is removed, like what a coronagraph does. So this is another way for describing this. It's called when you have just 2 mirrors, it's called a nulling interferometer. When you have 19 mirrors, you can do all sorts of really great things. You can make it not so sensitive to a single wavelength. It's what astronomers call achromatize. And the graph on the right-hand side of that image that shows the hole shows on a large range of brightness, each one of the tick marks on the left is a factor of 10, how deep you can make this dark hole where you can now look for the light of the exoplanet, which is many, many times fainter than the bright star. So that's a very cool thing. It means that our telescope is also our coronagraph. When you relax the telescope to look at bright stars and to find the wavefront based on the light from the bright star, I neglected to mention that. For this telescope to work, it always has to have a bright star in the field, because we're using the light from the bright star to make our coronagraph and to make our phase measurements actually work, because we don't have a stiff structure. We have to correct based on actual measurements. Okay, so the next slide, if you move your cursor around there, you can run the movie. Shows the light path into a planets. So there are a couple of nice things about this telescope that I really like. One is, does the telescope structure remind you of anything? It's a bicycle wheel. And you know what's really cool about a bicycle wheel?
It gets stiff as you spin it.
Well, we're not gonna spin this that fast. But the bicycle wheel is an example of what's called a tensegrity structure. It's a structure which is under tension, which has elements under tension, and it is the most efficient way, this has been mathematically shown, to produce a stiff structure with a minimal amount of mass. And that's what your bicycle wheel does. Your bicycle wheel is incredibly stiff, but it doesn't weigh very much because the spokes are under tension and they connect to a wheel and a central hub. So this is just a bicycle wheel, again, to decrease the mass and decrease the cost to make this work. And then the light that you see, those laser beams aren't obviously coming from space, but they show the chief ray off the center of the mirror, and they all bounce off of a single mirror for each one of the sub-aperture mirrors.
I'm not sure I'm on the correct slide now. What should I be seeing?
Go back.
forward?
It's just a circular, scalable interferometer telescope from off-axis parabolic elements, labeled the ExoLife Finder, and it's just an image of that telescope we've been talking about, and it has a background movie that you can play.
I'm not getting the background movie on this.
So move the mouse around it until you get you've got it's a funny thing. You're on a Windows machine, right?
Yeah. I'm not getting any animation on this.
But is the cursor, can you see the cursor in the image?
Yeah, my cursor, I'm moving it around the image of the telescope.
Okay, now if you click on it, what does it do?
Nothing.
This is the problem with animations always. Well, I can see it.
That's all it counts.
Okay. Well, maybe we can figure it out later. What it shows, if you see the telescope, it just shows an animation of the elements in the light path. That there's a laser beam that comes off of each mirror up to that core region where there's a separate secondary mirror for each one, and that secondary mirror is controlling the phases and the tip tilt and the pointing to a common focus. Sorry about that. Okay, so that's pretty much the story. This group on the next slide that is espousing these ideas is called the Planets Foundation, and as I said, it includes even amateurs. Casey Harlington was our first. He's sort of an amateur who wanted to push these ideas and got things started with the scientists that are involved. It is involved in building right now. We're in the process of building an off-axis telescope for nighttime observing on Haleakala, and that's a program which is in the midst of conventional polish of a relatively thin mirror. The Planets telescope that we're building think of as one element of the off-axis telescope, ELF, and that's illustrated in the next second to the far left panel. The ELF telescope is all about generating images of just a few exoplanets nearby, and the final step is something which could be done for less than $1 billion, is this notion that we should do a census and try to answer the question, can we help ourselves by knowing whether light really is fragile or difficult to find? And the last slide is just a summary. And that's what I had to say. So thank you for...
Do you have time for questions?
Sure.
Questions? Dick?
In your equation that predicted 38 times Fs, detections of civilization. How long are the civilizations? How long do the civilizations have to last? Is that forever after they reach our stage?
Yeah, so that, if you go to the 10th slide, which starts with the words counting extraterrestrial civilizations. So here's the idea there. This F sub S says, well, there are successful and there are unsuccessful civilizations. A successful civilization, by definition, is one that once it emerges, it survives to be observed by us over the next 10 years. An unsuccessful civilization is one that emerges and fades away. And so all of those numbers are multiplied together and end with this fraction of successful. And so we've torqued Drake's concept for the length of time that a civilization survives to suggest that there are just two kinds of civilization. Either they survive, maybe they go through the singularity and become something other than wet chemistry, biological life, but still call them successful because they use energy. Or they don't, and they wipe themselves out and There's no heat signature that is traceable back to life in that case.
Okay, so the answer is successful ones last forever.
Yeah, yeah. So they're just two categories of emergent life in this picture.
I had a totally different question, and I don't want to monopolize it, but I do have another question. Can you do anything, even though with the diffraction problems that you mentioned, with the upcoming big telescopes, 30-meter telescope? Can you do some of this?
Well, okay, so can you see slide 15? I kind of skipped over that one, I didn't.
Where were you?
15 doesn't have a label on it. It's a picture of the Keck telescope, the world's biggest,
That's it.
almost the world.
That's it.
Okay, so the Keck telescope is a segmented mirror, and in fact, all of the future world's largest telescopes are really derivative to Keck. They all maintain a stiff mirror by trying to link the edges. So that's a star. That might be animated too. Just animated through to the end. At the top left is a starlight coming into the telescope. The image of a star on the bottom right is what you get with a segmented telescope. Okay, so the problem is that each one of those telescopes has only a single secondary mirror. You don't have a chance of doing wavefront correction separately, except to keep the mirror surfaces co-aligned with edge sensors and stuff like that. There's a black spot in the middle of that image because it's saturated. But what you see is this halo of light, which is at about 1% or 10 to the minus 3, a tenth of a percent of the core brightness of the star. That's an absolutely horrible telescope to try to find an exoplanet, right? You're never going to do it. And while the TMT and the ELT have in their science goals to look at exoplanets, mostly that science is about looking at stars and sensitively measuring the effect of a transit, for example. The idea. So what ELF is about is to directly measure the reflected light off of the exoplanet. That's called the direct imaging problem. And the possibility of doing direct imaging with TMT and EELT, I'm sure it will be done, but it won't be done for habitable zone planets.
Okay. One more.
Okay.
One more question. The ELT or the big one, could they detect life on Earth from, say, I don't know,
Stellar distances.
yeah, some 50 light years, say?
Well, 50 light years is probably too far away. We've been using the example of ELF would detect quite readily images and biomarkers on Proxima Centauri, which is only about 4 light years away. The biomarkers, maybe not the imaging that I showed you, where you do the photometry and you use a computer to invert things, but biomarkers in the atmosphere, like oxygen and methane, would be detectable on probably a handful, and that's with a 30-meter telescope. Our argument for this telescope is that all of the other telescopes that are being built essentially have this scattered light that you see from Keck because they use the same technology. And they're designed to be able to see galaxies and have a wide field of view. So all of the objects we look at, right, are to look at a bright star and a nearby exoplanet. That doesn't require any field of view. So that's another reason why you can build a telescope which is also a coronagraph and do this dynamic range problem. I think the answer to your question and what's bothering you is, well, we're building all these big telescopes, why can't we do this problem with those telescopes? And the answer is they're not really coronagraphs, and they're not really designed to search for the reflected light or the direct thermal light off of exoplanets that are close to the star, which is the case for planets that could have life on them, like water-bearing planets.
Okay, thank you.
Okay, my question. in your inversion map of the rotating planet, how would transient phenomena like clouds and things like that confuse that map? It seems like it would be dependent upon a repeating pattern of thermal signature across the planet.
Sure. So it's obviously true that you could defeat this technique. Imagine trying to look at the surface of Venus, right? That just doesn't work. Venus is perennially cloud covered. We've done simulations where we put cloud cover, intermittent cloud cover in this, and if you want to learn more, there's a paper I can send you, Claude, that describes all the simulations. The answer is that it's pretty robust, especially if you're looking over several years. The effects of a transient cloud cover increases the overall noise, but it doesn't obscure the fact that you may have oceans or continents in general until the cloud cover becomes something like 50%. We've also used it to make images of planets like Jupiter. And it's pretty interesting that we can make pictures of banded planets and see a red spot, see structure in planets that are essentially not habitable, probably, but for which we may want to learn about what those exoplanets look like and are doing. The short answer to your question is that yes, you can defeat this, but in general, it's an inversion which is pretty robust. And the main effect is to increase the noise in the final recovered map.
Other questions?
One. When you have planets that are in the water-like, water-bearing zone of temperature, but that can vary from red giants to very hot stars, does the spectrum of the light change the probability or the chemical reactions needing to take place to create life would happen?
Yeah, that's an active area of research, which is where does life originate and how would it look different? So what happens, right, is in a cool star, the habitable zone is very close to the star. And in a very hot star, the habitable zone is very far away. So in some ways, hot stars you would think would be easier to see because the exoplanet is further away from the bright star. In many ways, it's not so easy because the planet is further away from the star, the amount of reflected light from the star is less. So it's likely that the first exoplanets that we make surface images of will be cooler stars. And there are also many, many more cooler stars than there are the hotter stars in our neighborhood. The question of what life will look like and how it would be different is something that I think that we're really just beginning to think about that. And this is this problem that we have only one example of life here. And every time we learn something new or increase our reach and what we can see, we find out how wrong we were. Right? Just go back 1,000 years when we used to think that we were the center, Earth was the center of the solar system, and then we weren't. Or then we used to think that the sun was the center of the Milky Way, and then we weren't. And then we used to think there was only one Milky Way, and then we're not. This process of discovering how unspecial Earth is and life here is I think the big lesson that makes it really hard to try and answer your question very confidently. But the comment I would make is that I think we'll be looking at redder stars, cooler stars, sooner than we're looking at sun-like stars. And it's almost certainly true that life will probably be different. Most people believe that water is such a wonderful thing to make life happen that we still think in terms of water-bearing planets as the place to find life, but maybe that's wrong. Those are all really interesting questions, and we can only get to them by building optics that are able to separate the light of the exoplanet from the light of the star.
Anything else? Would you care to make a comment about, you were just mentioning red dwarfs, but red dwarfs tend to be flare stars. Could you make any comment about that?
Yeah, I know. So the Proxima b has two apparent strikes against it for having life. One of them is that the planet is so close to the red dwarf, it must be, if it's going to have water, be warm enough. And red dwarfs are really active. You guys worry about flares on the sun, and the flares on a red dwarf are thousands of times more intense than Carrington events that we think happen to the sun. The flip side to that, though, is that it could well be that, well, there's some people who think that a radiation environment is the most important ingredient to evolution, accelerating evolution and creating robust species that are capable of adapting to that environment. Another part of the answer may be that, well, if it's tidally locked, then there'll be zones. You can pick your poison by being on the far side or being near the terminator or near the pole. And those zones don't have to suffer the diversity of the day-night variation that exists between being nearby or not. One of the arguments for life having a hard time on the Proxima b, the exoplanet around Proxima Centauri, is that it could be that the atmosphere would be driven away by that radiation. But it's not at all clear. That's a devastating problem too, because atmospheres are transient. And so if there was water and if there was an atmosphere, the kind of toxic environment of lots of radiation might, in early phases of M dwarfs, lead to an atmosphere, but it would come back, as atmospheres, I think, tend to do. So there are lots and lots of unknowns, and you're right, it's likely that life will end up being different there. But it might well be that, just in terms of its energy consumption, it's still detectable as a signature that we could map. Now, I should say that we talked about, when we did this rotational inversion, we talked about planets that both rotate and orbit. The same ideas actually work if the planet is tidally locked. Doesn't have to have the axis oriented 90 degrees, but over many orbital periods, the reflected light that we see off the planet is varying because of the seasonal variation. So even if it's tidally locked, we can, on the side of the planet which is illuminated, we can deduce structure and see it.
Yeah, Dick?
I have a down-to-earth question. Since Proxima b is far south, would you be building this telescope in the southern hemisphere?
Yeah, our benefactor in the early days has a plot of land in the mountains in Chile. And if this was built as a private enterprise, as it almost certainly would be, it would go in the south, probably. But I have to put a caveat to that, which is that we think that Proxima b is not the only place where we would look. It's the largest signal for doing these imaging of exoplanets, but it's not the only exoplanet that we would. There's probably a handful of about 6 or 7 systems that we could make images of the exoplanets with.
And that's with the ELT, not the
the ELF.
The ELF, yeah, EL.
Yeah, that's right.
Okay.
Anything else? Well, if not, let's thank once again.
Yeah, it's very
Jeff
interesting.
Kuhn. Thank you so much.
Well, thanks for listening.
We really appreciate this, and hope to see you out here in Big Bear again one of these days.
Oh, I'll be there.
Okay. Take care.
Take care.
Thanks, Tom.